Yeah, so welcome back again. So, the topic that we are going to learn today is the arch terminology. So, when we talk about the arch terminology, we have seen different types of arches. We have seen different shapes of arches, in fact. We have seen the materials used in arches, and we have seen why arch is comfortable for long span structures compared to a beam. And now let us try to understand the terminology associated with an arch. Okay. So if we can try to see this, this is how in reality an arch is generally constructed. Okay. So you can see that a curved portion or a bent up portion, as we have seen the definition, and the arch is supported on two abutments. So two abutments, you can see the abutment here. So what exactly is an abutment? Abutment is the end point of an arch, the kind of support where the arch would rest. And then we have the crown, that is the topmost portion of an arch, which is defined as the highest part of extrados. The highest part of extrados. So what is extrados? So this specific portion is extrados. So it is the outer curve of an arch. Extrados is the outer curve of an arch. And like that, we have the intrados, which is actually defined as the inner curve of an arch. So external curve and internal curve, or outer curve or inner curve. And then we have the spring line. You can see that here. This is the spring line. That's a major arch. What is that? It is an imaginary line joining the springing point of either ends. So springing point. So what do you mean by springing point? These are the points from which the curve of the arch spring. So you can see the action here. It's an imaginary part. So spring means this specific line that is being considered. What all we have? We have the soffit. So soffit is inner surface of an arch. We need to understand the difference here. Inner surface, inner curve. Okay. Inner curve is intrados, inner surface is soffit. And then we have the skew back. You can see that skew back here. So what is the skew back? It is the inclined surface on the abutment. You can see that. So this is an inclined surface. So this inclined surface is the skew back. So now the other important aspect associated with the terminology of the arch, you can see we have seen springing line, springing point, and then what all we have? Of course, we know what is the rise. It's the vertical distance that is under consideration for the arch from this point. You can see this is a horizontal point. So from the baseline to the mid of intrados is called rise. Okay, so we have seen soffit, arch axis is known. So this is the depth of the arch. So span is the, so there are two. So span is, one is outer to outer distance between the abutment, and the length is this center to center distance between the mid portion of the arch, when you try to put it like that. And other terminology, the other portions that we are trying to consider here is, see here, in a realistic arch, I've just sketched it. I've brought it from one source, from an isometric sketch of a portion of a brick arcade illustrating the terms. So that you could see here carefully, you can see a term called key. So a key is the topmost portion here. It's a wedge-shaped unit fixed at the crown of the arch. You can see here. So this is a crown and it is fixed. So that is how we use it. And you can see that this is the haunch. You can see that small portion there. This is the haunch. So what is the haunch here? So haunch actually is the lower half of the arch between crown and skew back. You can see here. So this is a haunch and this is the crown. Between crown and skew back, we have a portion called as an haunch. So like that, each and every term associated, and you can see this also. voisers. You can see these voisers. So what are those? These are the wedge shaped units. So a wedge, it's a shape, so that are provided throughout this entire portion of the arch. So one should know the terminology to understand the behavior in a careful manner. And you can see this is a spandrel. So this is like a curved triangle. You can see here, isn't it a triangle? This is like a triangle, right? But it's curved in shape. So curved triangle space between extrados, that is the top portion, and the horizontal line, and the horizontal line, that is called as spandrel. So all the terminologies associated with the arch has been covered, and this gives us a very good thought-provoking ideas in terms of see how these shapes would work: a two-hinged arch, a three-hinged arch, a fixed arch, or there are other shapes as we have spoken in the last previous sessions. Okay, so this is about arch terminology. So moving forward, we have seen it yesterday. We have understood the concept that in a three-hinged arch, we will be having an internal hinge. We will be having an internal hinge, and because of the presence of internal hinge, we will have the flexibility to take the additional equations of equilibrium equation. Additional equations of equilibrium equation. So that is why the total reactions are 2 here, 2 here. So total 4 minus 3, that is number of known equations, minus 1 due to internal hinge. That is what we call it as a determinate structure. That's why it's called as determinate structure. And these forces at any given section, if we cut it at a section point D, you will have this as the axial force, this as the shear, and this is the moment at any given section. And when we are trying to analyze an arc, we need to calculate the behavior of arch by cutting a section at a point. Okay, yes, okay. So similarly, when we move forward, we get into two-hinged arch. So this two-hinged arch, again, as I said, it has two pins here. So this is one hinge, and this is also one hinge. Okay, so here two reactions we have got, and here also we have got two reactions. So the total reactions are 4, and we have three known equations, and the degree of indeterminacy is 1. Degree of static indeterminacy is 1. So now when we consider that, this is a statically indeterminate structure, and the understanding that we need to get is the analysis is a bit different compared to three-hinged arch. So three-hinged arch can be solved using equations of equilibrium, but when we go to two-hinged arch, it might not be directly possible to do that. Okay, so as I said before, we have 4 reactions and unknown reactions, and there are 3 possible equations. The degree of static indeterminacy is 1, as I have said before, and if at all, if there is any load acting, and if we cut a section here, see what is happening. So we have the normal thrust or the axial thrust, we have the shear force, and we have the bending moment. So this is similar to what we have seen in the three-hinged arch, but the analysis process would be different. And as I said here, this this normal thrust and this is making an angle theta with the horizontal. And now, in order to solve this problem, which is a statically indeterminate structure, we need to make use of the strain energy concept. So strain energy due to bending and strain energy due to axial force. So whatever the concept that we have learned in strain energy due to axial and bending theories are pretty much applicable here. So we already know that strain energy due to bending is given by the expression integral m square by 2ei into ds, and for axial force it is P square by 2AE into ds, where EI is combinedly called as flexural rigidity. Flexural rigidity is a terminology, and AE is called axial rigidity. AE is called axial rigidity. Okay, so these both are actually very important to decide the overall behavior of the members under consideration using the strain energy concept. Now the total strain energy will be the combination of bending and axial, isn't it? Because it is undergoing axial force and it has bending also. So therefore the total strain energy is combination of these two. Now what does Castigliano's theorem says? Partial differentiation of strain energy with respect to the applied load or with respect to the load will give deflection. So here, initially, the Castigliano's theorem can also be represented in terms of principle of least work, which states that partial differentiation of strain energy with respect to the horizontal force is equal to 0. Okay, so there is a very good derivation or the concept behind theorem of least work. Once we, in the coming sessions, when we learn the in detailed concept of two hinged arch, I'll be thoroughly explaining it there. But otherwise, so you can see that partial differentiation of strain energy with respect to H, isn't it? So m square by 2EI, so partial differentiation. 2m by 2, 2 will get cancelled, m by EI into dou m by dou H. Fundamental basic differentiation. Like that, this also. P or this is also called as n square. So this is n by AE into dou n by dou H is equal to 0. So from this, actually, there is a question that strain energy due to shear also can be considered, but it is very small. The strain energy due to shear is very small compared to strain energy due to bending and axial force. That's why it is neglected right now. Okay. Now, so once we solve this, we'll get the expression or the value of H. And once we get the H, that is how we try to get the unknown parameters of an arch. Okay. So this is how we try to analyze a two hinged arch. Okay. Yeah. So now let us try to see the next topic, that is linear arch and Eddy's theorem. Okay, linear arch and Eddy's theorem. So this is one of the very important concepts for us to understand, to visualize and think what exactly we are trying to do with the arch. Okay, so let us try to take an example of an arch, an original arch with any good shape, parabolic, whatever it might be, and let us subject it to various loads. Various loads. So this is A, this is B. So you have different loads here. Okay. And let us also try to take some supports like both ends pinned like that, such that we will get to know what are all the reaction components acting there. Okay. So this is H, this is A, sorry, RB, HB, RA, HA. So if you see this, this is how exactly an arch would look like. This is exactly how an arch would look like, the original shape of an arch. So this is called as actual arch. So this is C, D, and E. And you can also say that there are some, let us divide this arch into various portions. P, Q, various portions, that is P, Q, R, and S. So the entire arch is divided into 4 portions. Okay, and we have the center or some portion. Let us take some section X or Y as and when required. But this is how an actual arch would look like. So you can see that actual arch. Okay, first let us try to talk about actual arch. So this arch, whenever we say actual, it follows either a parabolic shape or a circular shape or an elliptical shape, and which has the flexibility that it can be constructed easily with aesthetic appearance. Okay, with aesthetic appearance. So the arch, so as I said, what is that? It has got different shapes, right? So the arch which follows either parabolic, comma circular, or elliptical shape, elliptical shape, and can be easily constructed, and can be easily constructed with with aesthetic look. Means, you know what is an aesthetic look like? Aesthetic look or appearance is called as an actual arch. Is called as an actual arch. So what does that mean overall? So when we say the actual arch, so it has got some shape which is acceptable and some looks to get it, like the appearance to the external world. So that is how we actually define an actual arch. Now, so this is our real scenario, but in actually we need to understand how did we arrive at this shape of parabola or circular or any other elliptical shape. So for that there should be some background theoretically. So that concept that would talk about the theoretical behavior of arch is called as an linear arch. That concept that would talk about the theoretical behavior of arch is called as linear arch. And that linear arch is actually takes a different shape in the form of a polygon, and that polygon shape is funicular polygon. What is that shape? Funicular polygon. And the theorem associated with the calculation of bending moments in an arch is Eddy's theorem. So right now we have seen actual arch. In tomorrow's class, we will see what is a linear arch or theoretical arch, how did we arrive at that, what is Eddy's theorem, and what are the expressions that are required to analyze a three-hinged arch. Okay, so thank you all and see you in the next class.